All right, let's do part 2 of section 1-4, which is on continuity and one-sided limits. All right, now the continuity of each function at the given x value. Okay, so if f of x equals x squared minus 9 over x minus 3, think about what's going to happen with that when you plug in 3. All right, it's going to form a straight line, but there's going to be a hole at x equals 3. This is an example of a function that has what's called removable discontinuity. All right, this is a point on a graph that is undefined or does not fit the rest of the graph. And in turn, there is a gap at that location when you are looking at the graph. It could be filled in, meaning you could define another function in order to fill in that particular value. So that's why it's called removable discontinuity. All right, now let's look at our example right here. In this case, it says discuss the continuity at each function on the given x value. All right, so the question is, if we were to graph this, as a matter of fact, here's what we're going to do. I've already set this up on my calculator. You can do the same on yours. So we'll go ahead and we'll set up, actually I had them set up. For some reason they got erased, so let's go ahead and do that. Let's type it in. 1 divided by, in this case, x minus 1, and I graph it. Okay. So the question is it continuous when x equals 3? Let's look at the table. If you look at the table, it has a value, so yes, it is continuous. At that value, it is continuous, so yes. So yes, it is. Yes, it is. All right, now, let's go back to the original function that we had just a moment ago, and let's clear it out. And let's type in x squared minus 9. And you can do this on your calculator at home or wherever you're watching this. All right. And then if you hit the graph button, just like this, you're going to get a line. But if you go to your table, you will notice that there is an error at x equals 3. That's that hole we talked about. It's going to look something like this. All right. So the question is it continuous? The answer is no. It is not continuous. Not continuous. Open dot. All right. Now, and let's try the same thing again. And actually what I'm going to do is I'm going to save this equation because I'm going to need it here again in just a minute. So let's type in 1 divided by x. I always mess up on these graphing calculators, so you have to bear with me. All right, 1 over x. And I hit graph. Okay, now the question is, it says for every value except for 0. And then when it's not 0, it's going to have a value of 2. So the question is it continuous? Well, let's look. At 0, there's an error value, but it still gives us a value of 2. So what's going to happen is the curve is going to look something like this. It's going to look like this. It's going to look like that. But then when at x equals 0, it's 2. Is that continuous? No, it's still not continuous because the limit is not the same as the value at x equals 2. So it's not continuous. And you can look at it by graphing it and see that it's not continuous. All right, now, I'm going to go ahead and I'm going to delete this one right here because I no longer need it, but I do want this one on there. And when I graph it, now this time, we're stating that x is not equal to 3, but at x equals 3, we're stating that it has a value of 6. So the question is, does it fill in the value? And the answer is yes. It does fill in the value. The above value. So right there, we had an open dot. But this right here, this 6 here, filled it in. So now, excuse me, if you look, this is an example of removable discontinuity. This is where the graph, it was undefined, but it did fill it in, so therefore it has been filled in. All right, I'm going to pause this for just a second. All right, on your own, you can say, how would you define the word continuity for this course? How many requirements are there for continuity? What's a special limit technique? And provide one graphic example. You can do that stuff on your own. All right, we're going to talk next about what's called the intermediate value theorem. Okay. Now, the intermediate value theorem, this is the book definition. It says if f is continuous on a closed interval from a to b, and k is a number between f of a and f of b, then there exists at least one number such that f of c is equal to a value of k. All right, that doesn't make a whole lot of sense right there. So we'll go to the next page, and I'll show you a little bit more what that means. All right. Okay, now, if you were to graph this curve right there, matter of fact, let's do that. Y equals, let's clear it out, and that's going to be x to the third plus 2x minus 1. And if we graph it, here's what it's saying. Okay, at 0, all right. The curve does this. And if you look at the graph, it goes through here. It goes through there. But at some point, it crosses the x-axis, meaning that somewhere it has a 0 value. What the intermediate value theorem says is this, and I'm going to write this down, f of 0 equals -1 and f of 1 equals 2. It's saying that somewhere in between there exists a value between 0 and 1 such that f of c equals 0. It's not stating what c is. We don't know what c is. It's just saying that there exists. The intermediate value theorem says that there exists a value somewhere between 0 and 1 where the curve crosses the x-axis and has a 0 value. All right. Now, I'm going to do this one real quick. Okay, -1 and 1. That's what the curve looks like. The question is Is it continuous? The answer is no, not continuous. It's not continuous because the limit on the right does not equal the limit on the left. Let me rewrite that again. Limit on the right does not equal the limit on the left. It would have to be in a defined setting or defined range. All right. You can go ahead and work 3 on your own. See what you come up with about that. See what you can come up with, and we'll talk about it at a later time. In the meantime, for this Friday, which would be the 21st, by 11:59, you need to email me, either share with me all this on a Google Doc or email me a picture of what it looks like. Just send me a picture, and then I will look at it. All right.